Hello and welcome back to our discussion of the interference with electrons in the double slit experiment. So in the previous two videos we did two things. First of all, we derived an expression for the position of the maxima in terms of the wavelength. So just to go back to look at that, in the first instance, source of electrons, coherent beam of electrons, coherently split into two equal parts that travel over a distance to a detector D, and you get constructive or destructive interference depending on the phase difference between psi1 and psi2. So we've seen in the first of these three videos that if D is the distance between the slits, then the path difference here between ray 1 and ray 2, or wave function 1 and wave function 2, is d sine theta. And we've seen that d sine theta is equal to a whole number of wavelengths. If it is equal to a whole number of wavelengths, the waves arrive in phase and you get a maximum, where m is an integer. So that's what we did in the first of the three videos. In the second video, what we did is we showed that the probability density, and hence the intensity, so the intensity is proportional to the probability density, we saw that if we coherently split these two wave functions, we got the following result. The probability density went as 4a squared cosine squared on delta theta on 2. Just to remind you that the first wave function, psi1, describing the electron traveling from the source through slit 1 to detector D, was given by A. The second wave function, which describes the electron having gone through from the source through slit 2 and been equally split by slit 1 and 2 and then proceeding to the detector D, is given by A, E, the I, theta. Now, in fact, what we did is we measured the phase difference between the two. So I've called this delta theta. And delta theta is the phase difference between the electron wave functions 1 and 2, or 2 and 1. And I set this one equal to 0 as a reference, so the phase difference is really just the phase of the second wave function. So what one can see is that the intensity, the number of electrons that are arriving, is directly related to the phase difference between the two wave functions. So what I'd like to do is use this result to show that you get exactly the same result that we obtained by geometric considerations. So for a maximum, we would like this to be a maximum. So cosine squared will be a maximum when this argument function here, when delta theta on 2 is equal to, well, if I put 0 there, I get cosine squared of 0, which is clearly a maximum. It's 1. So let's have 0. If I let that equal to pi, then cosine of pi is minus 1, but the square of it is 1, so pi is fine. Likewise, 2 pi, and so forth. So I can write this as m pi. If m is equal to 0, I get 0. If m equals 1, I get pi. If m equals 2, I get 2 pi, and so forth. So this shows that the integer m is just 0, 1, 2, etc. So that's great. We've already seen that we've got the integer that we obtained by geometric considerations. So what we'd like to do is relate the phase difference to the path difference. Well, there's a very simple relationship, and it goes as follows. The path difference divided by the wavelength is exactly the same as the phase difference divided by 2 pi. Now what this means is something very intuitive. If the path difference is actually equal to 1 wavelength, that means that the phase difference must be exactly 2 pi. Because a path difference of 1 wavelength means you've gone through 1 complete cycle, or 360 degrees, or 2 pi. If the path difference was half a wavelength, then the phase difference would be half of this, which would be pi, which means that you've gone through half a wavelength, and in fact the wave will be inverted. So we now know that the path difference, d sine theta, because there's the path difference here. So this is d sine theta is the path difference of wave 2 with respect to wave 1, divided by the wavelength must be equal to the phase difference. Well, the phase difference is delta theta on 2. Or in fact, if I rearrange this, the phase difference delta theta is actually equal to 2m pi. So in fact, the phase difference is what I'm interested in. I'm interested in the phase difference delta theta between rays 2 and ray 1, or wave functions 2 and wave functions 1. So that's equal to delta theta on 2 pi. But we've seen from this relationship here that the phase difference is just 2m pi. If I divide through by 2 pi, this just gives me m. And if I rearrange this, I get the following. D sine theta is equal to m lambda, which is, of course, the relationship that we got from purely geometric considerations. So to recap, the notion of interference with particles, in this case we've discussed electrons, but it could be protons, neutrons, atoms, or even molecules, is predicated on the quantum mechanical description of the wave by a wave function. If we have a source of particles, a coherent source of particles, and the particles are incident either many at a time or one at a time on a double slit, then that wave function, which describes the particles as coherently split, and the superposition of these two wave functions will determine whether you have a maxima or a minima, which depends on the phase difference between the waves as they travel this distance and arrive at the detector. And this phase difference is related to the path difference, and therefore we get this relationship d sine theta equals m lambda, where m is none other than this integer. So we'll leave it there. What we'll do in the next video is we'll confront full-blown quantum mechanics by looking at the Schrödinger equation and solving it for some simple systems.